in the whole proof of the Grothendieck conjecture. And I think I hope it's okay for you that I don't give an overview of everything we're going to do, but just concentrate today on one small detail. But I want to attach a little philosophical remark to that. I discussed with you how you can do mathematics, namely build a big machine and feed in the problem and just wait what comes out. And sometimes that doesn't work. And I have an advice for you, and of course you shouldn't take advices, but let me still try to do it. If you do mathematical research, first of all you should remember what one of my sons said. My sons in Dutch said, "Ik mag zelf weten wat ik wil." I can decide myself what I want. So you're responsible for your research, and let nobody tell you what to do, and even more important, what not to do. Never follow that, just follow your own taste. So that's my first advice. And my second advice is, sometimes mathematicians impose on you, the elder ones, the elephants, that you really have to do abstract things, and that's the best, and that's the highest state of the art, and so on, and so on, and so on. Now, many mathematicians in the back of their paper have a lot of computations, but usually they don't show it anymore. And they really have to tell you, well, I did a lot of stupid computations, and they were really necessary to really achieve this. So please don't hesitate yourself, if you're doing research, to spend now and then an ample amount of time in just sitting down and feeling what the ground is under your feet. And you know yourself best what you have to do. Either do computations or do a special case or whatsoever, or write out a small detail in the proof completely, and so on and so on. And the most important part about this is to economize. So the bad thing is that you spend all your life in doing very high abstractions without ever knowing that 57 is not a prime number. The other bad thing is to do only stupid examples and never know any general theory. So the important point about research is that you really make for yourself a balance between this. And sometimes step back and make a list. What did I do? Spend 3 weeks on computing this example. Then be very satisfied with itself, but then close it and then go to some more abstract things. So you really have to balance that, and that's one of the main things in doing research. And what is the reason I'm giving this talk today? Not only that I was asked to do it, but the reason is that I want to show you one of the nasty computations which goes in the proof of the Grothendieck conjecture, and really show you what that computation does for you. And I worked on this for I think 7 years and got nowhere. And Johan de Jong, who was one of my students, when I got stuck completely again, I took off sabbatical and went to him for several months in Princeton. And he listened patiently day after day to all my stupid computation, and he never criticized me for being so stupid or missing the main point. But I really wanted to do the computation. And today I'll show you one of those computations as an exercise to convince you that the theorem should be true, but also to convince you that if you have to do it only by computation, you really have a lot of difficulties. Okay, so the first point is the main reference of today is the paper 43, which we always call purity. And there are two parts of the paper. One is a very abstract proof of an abstract theorem, and one is a concrete application of that theorem and then doing the computation. And I'll show you both, but not the abstract proof. So this is joint work with Johan de Jong. And let me tell you, tomorrow there will be 2 talks by Cheng-Li and myself. The titles of the talks are as in the notes, are as on the website now, but are interchanged in the old program. So we decided to interchange the 2 topics. So tomorrow, first hour, I will talk on the proof of the Grothendieck conjecture, and Cheng-Li will talk the second hour in density. And so that is opposite from what is in your printed version of your program. Okay, as usual, you know there's something hiding. but I'm not hiding anything which is not already in the notes today. So you remember the picture I had, right? I have some Newton-Polygon stratum, and I have another Newton-Polygon stratum which is in there, and here the A number is at most 1. And my proof was yesterday to move out from a point here to a point there. So yesterday I proved you the theorem that if you have a DNA module which has A number at most 1, that's the DNA module of a p-divisible group, then you can deform the p-divisible group to any given Newton polygon which is below at a given one. And that's the kind of machine, that's the kind of automatic thing. And once you know this place, you just write down whatever you like. And today and tomorrow, I'll prove you this. So what is this thing? This is theorem 7.1. And theorem 7.1 says that if I have a p-divisible group over any field, then there does exist, and perhaps we have to take this algebraically closed if you want to be very precise, but that we don't care for the moment. It's not necessary, but you can assume that. It doesn't make any difference in generality. Then there does exist a p-divisible group of some integral base, everything is in characteristic p. There does exist a k-rational point such that the special fiber is the one you start with. So that's in this, possibly in this very singular locus. But the generic fiber has A number at most 1, and the Newton polygon is constant over your whole base. Yeah, so you can deform, keeping your Newton polygon, but making the A number at most 1. Now let me make a remark. The A number of mu p infinity, of course, is 0, and the A number of qp mod zp. So why did I write at most 1? Suppose you start with mu p infinity, right? Then I certainly cannot deform it to something where the A number is 1, because the A number is 0 and it's approximately continuous. So if I would write A number equal to 1, this theorem certainly would be false, right? So this just says that if everything is ordinary, there's nothing to do. It's just okay. But as soon as this is not ordinary, then the A number of this closed fiber is positive, and the A number of the generic fiber is 1, because the Newton polygon stays constant. Okay, so this is just a matter of notation. Now, today I will only prove this theorem in a very easy case, it seems, namely in the case that your closed fiber is geometrically simple. Some people call it simple, some people call it isosimple. So this means that if you take a p-divisible subgroup of it, it's either 0 or everything. And let's call it simple. And tomorrow I'll show that if I want to prove the full theorem, that this case of the simple case is very difficult, but that the general case is a complete formality after you know the simple case. So today we really do the hard part, and tomorrow I just relax, and I hope you can relax too, and we just do the general case without much difficulty. But that's for tomorrow, and then I'll show you that. Okay, in order to prove this, yeah. If the Newton polygon is ordinary, the A number is, Yes, yes. Is positive. And the reason is, up to the classification, you can write it as a direct sum, a product, up to isogeny. And up to isogeny, and a number which is positive stays positive. So if the slope is not 0 and not 1, then that isoclinic part is local-local. Yeah. Yes? Okay, let me give you a few remarks. First remark is, it's not in the notes, but it's not difficult. If X is isogynous to a product of G, Mi, Ni, then the A number of X is at most the sum of the minimum of Mi and Ni. And I leave this to you as an exercise. And next exercise, which is slightly more involved, you have the values Ax and this number, yeah, and I want to show, yeah, let's say at least one Mi and I is not 0, 1 or 1, 0. Then I have this equality. In exercise, is all values show up. So if you take the class of all p-divisible groups isogynous to a given one, the A number may go up and down, but all values show up. And this exercise is not difficult. This exercise after today is an almost triviality. But it's easier if you have some techniques developed. Okay. In order to prove this, I focus on the basic assumption that M and N are two integers with greatest common divisor M and N is 1. And you might write here equal, but I don't care so much for that case. And you see, if I prove the theorem for GMN by duality, I prove the whole theorem for GNM. So this is the most general case to study. So this will be the blanket assumption throughout today. And yesterday you saw, was it yesterday? 2 days ago, Jingli Chai defined for you the group GMN, and I might stress that this group is defined already over Fp, and it's given by the DNA module like this. It's the DNA module ring times the left ideal, which you get by dividing out Vn minus Fm, and that's the DNA module, and that, by the theory over a perfect field, defines you this p-divisible group, and this is this p-divisible group. Now, let me show you how, and I do that because I wanted to make a remark on notation. You have the following exact sequence. For any p-divisible group over a characteristic p field. Now let me change, Jingli, I hope you don't mind, let me change notation for the DNA module functor in this way. So now the boldface D is the DNA module functor, not to get mixed up with other things. Okay, now I take the DNA module functor on this exact sequence, and what I get the DNA module of X. Then I get the DNA module of XP, and this map is the DNA module functor applied to F. Now the first thing you prove is that this is injective. And the basic reason is that F divides P, and multiplication by P on a free module over the lead vectors is injective, so certainly this is injective, right? And now you can replace this by the DNA module of X by just changing constants. And then this map right? It's the same as this map, and now it is the sigma inverse linear map, and that we denote by V. Now, I'm taking the habit of making F and V script as soon as I work on the DNA modules, and straight if I either work with group schemes or with the DNA module ring. So V is the Verschiebung operation, it's sigma inverse linear on the DNA module. And you see the reason that I distinguish F straight and F script for this way. Okay, so then you have an exact sequence of left modules. And what you easily prove is that this is the DNA module functor of XF. Right? Now, clearly, the dimension of this over your field, over the Wheat ring, I mean, the Wheat ring kills, P times kills this. So this is a module over the Wheat ring mod P. So that's a module over your residue class field. So that's a vector space. And this vector space has a dimension, right? And that's this dimension. And you immediately see that this dimension, of course, is the dimension of your p-divisible group, because the tangent space is hidden in here, right? So the dimension of your p-divisible group, right, is the dimension of this mod Vm, right? And now here I still have a V because it's in this Wheat ring, but this soon will change the script V's. And that's M in this case, and then the GMN is simple, that's easy to see. And that follows from the property that the greatest common divisor is 1, and you have this duality. Okay, so what we do today study all X isogenous to GMN. M and N are fixed now, and that's what it is. You remember what I said some time ago? P-divisible groups partly feel like algebra, or like a cohomology group, or something like that. If you have a p-divisible group which is defined over some large field with lots of transcendentals, then up to a finite map, it is isogenous over the algebraic closure of that field to something over the prime field, right? So, which is certainly not a geometric property. If you have an algebraic variety or anything, right? There's no reason that a finite cover all of a sudden should be defined over a finite field or even over Fp, right? So geometric properties of your varieties are really important that you stick to your field of definition. But for p-divisible group, this is completely different. So on the one hand, you should feel this as an algebraic object that feels like some cohomology group. On the other hand, you'll see today that there is geometry, there are moduli spaces, and then you get a completely different feeling. Okay, now, in order to do this, I will first do some notation. In this case, I define the number 2r by m minus 1 times n minus 1. Yeah? Now, if you have equality here, then m and n are 1 and this is 0, and everything is not very interesting. Okay, so this is a blanket assumption also in the whole case. I will define for you a new group scheme, HMN. And the definition is as follows. So let me first state the definition, but you won't be very happy with it, I'm afraid. The DNA module of HMN will be given as a direct sum of W times EI, where I runs from 0 to H minus 1, H is M plus N. So that's a W module free of rank H, right? this is over Fp. So now I first start with Fp as a base field, and I have the following equations. F of EI is EI plus M, and V of EI is EI plus M. Yes? And you all agree that this gives me a nice Dieudonné module. I mean, I've described you for all base elements how V and F operates, and I work over a finite field, so F and V are really linear, right? Because the sigma is the identity in this case. So now I have defined for you certainly a very nice p-divisible group, right? And it's easy to see that HMN is isogynous to GMN. How do I do it? Well, you take the Dieudonné module, which I get by W times EI, where I is in the semi-module, the semi-group, generated by M and N. Yeah? Now, if you take the Dieudonné module of this, you easily, if you take this, you easily see that this is the Dieudonné module of GMN. Just see, the Dieudonné module here, right, is generated by one element, which I call E0, right? And then F of E0, I can baptize E0 plus N. Did I? Oh, sorry. I always mix these up. Then, little h is the height. That's M plus N. Yeah. And so you see that this Dieudonné module is generated by all VF multiples of E0, and if I baptize them in this way, I perfectly get everything, and you easily show that this Dieudonné module is exactly this, right? If you apply M times plus N and N times plus M, you get the same index and you get 0, right? So you see that this really is contained in the Dieudonné module of HMN. And in this Dieudonné module, I should like to single out a very specific element. So, what's my notation? I take beta m plus gamma n is 1. After all, beta and gamma, after all, m and n are relatively prime, so I can choose positive integers, such that the combination of m and n is 1, and then I take the smallest beta and gamma who are doing this. So beta is strictly between 0 and n, and gamma is strictly between beta and m, right? And now what I can do, I can take the following element, pi, which is f gamma phi beta. Yeah? And as I'm going to do a special example, I will do the special example. M is 5, N is 3, F EI is EI plus 3, V EI is EI plus M, and here of course you see that minus 5 minus 1 times 5 plus 2 times 3 is 1. Oh, I said positive. Sorry, I didn't mean positive. Arbitrary integers. And then the pi here will be the f squared v to the minus 1. Now that seems a very nasty thing, but of course I can easily show that this is the same as I can take p to the gamma, and p to the gamma is f gamma v gamma, and then v beta minus gamma. And it's also equal to p beta, and then f I get gamma minus beta, I guess. Okay, so now one of the beta and gamma is positive and the other is negative. So you either use this or you use this, that you have a true Frobenius, and then you divide by p. And everything I'm saying here is that pi is in the anamorphism ring of HMN, and now I want to add that I really work in FP. And I leave it as an exercise to you to show that pi to the h is p. Yeah, so what you do, you take this form, you raise it to the m plus n power, then you get 4 terms. You use these two equations to say something about m times gamma and something about gamma times n, and then you sort out the terms and you see that you exactly get this. Okay, so what I know, that this ring, of course, is commutative, and what you easily show is that this is a discrete valuation ring, right? And now the definition, and now I take HMN. Now I tensor up with some field K, and I assume that my K contains Pm plus N. Then I'm going to study this anamorphism ring. This is a subring of the anamorphism algebra. Right? And what I claim is that this is a division algebra over QP, that its degree, the degree is m plus n, is h. And you can easily compute the invariant, and the invariant either is n over h or m over h according to your normalization. There are different normalizations in the literature for the Brouwer invariant of a local field, and I don't want to go into this case. And now the important point comes. This is the maximal order in this algebra. Yes, please. Excuse me? Yeah. Yes, I would like to. Yeah. So is this what you want? P I E is I E plus 1. Is that what your question was? Okay, yeah. Pi to the h? No. No. It is multiplication by p. So you have your DNA module, which is free of rank h over w, and pi in each component multiplies by p. So it pushes down all. So yeah. So pi to the h of EI is p times EI. So it defines, so the image of pi to the h is the DNA module p times the DNA module. Did I understand your question? Did I answer? Okay, now if you don't like my construction, you can do the following. You take this ring, and of course this ring is equal to the endomorphism algebra of GMN over any big field. Yeah? They're isogynous, so the endomorphism algebras are the same. And now you can ask the following: does there exist a p-divisible group such that its endomorphism algebra, that it's isogynous to this, but its endomorphism algebra is the maximal order in this division algebra? And so I could restart and say, well, my HMN is the unique group over an algebraically closed field such that each endomorphism algebra is the maximal algebra. Right? Then there's a little remark which is in the notes, and perhaps you're a little bit, you find it a little bit strange, but soon, where is it? I can't find it so quickly. So, remark easy. For any x isogynous to GMN, hence isogynous to HMN, there exists an isogeny phi from HMN to x such that the degree of phi is exactly p to the r. And I'll soon show to you how you prove this fact. You see, if you have something which is much smaller than p to the r, for example, the identity on HM, you can always multiply by pi to get the degree multiplied by pi, and then after doing it r times, you get this. And r is exactly that number there, right? And now, construction. T, which is Tmn, but I omit the m and n from now on, is the moduli space of all phi mapping HMN to x such that the degree of phi is p to the r. Okay, so you know how to do that. I mean, you take a base S, you take the product of HMN, cross that base, then you have some finite group scheme which is flat over the base, which is sitting inside m times mn over that base. That finite group scheme has rank p to the r, and you form the quotient. The quotient is a p-divisible group over S. So here the variables are x as well as phi, right? That defines your functor, and that functor is representable. Now, why is it representable? That's easy, because this map is given by this kernel, right? And that kernel is a linear space into some algebra, say, of HMN square brackets p to the r. It's certainly in there. So it is a linear space in some other linear space of fixed dimension. So it's a point in a Grassmannian. Now, not all point in a Grassmannian do, but you moreover have to assume that the group structure really makes it a subgroup. And well, and that you all perform. So it's a point in the Grassmannian which has certain properties. It's closed in that Grassmannian. So not only this modular space does exist, but also the modular space is proper. Now please note that this is completely different from deformation theory. You see, we have a very good functor of deforming p-divisible groups, right? But that always gives you a local structure. And this really is a global thing. Okay, now the main theorem is, and that's the main theorem in the whole, what I'm doing. So what's the number? That is 7,7. The space T, which I've constructed here, is geometrically irreducible. And that's what I'm going to prove for you. Now, remark, this immediately implies, the theorem I want to prove, this immediately implies 7,1 if x0 is isogynous to GMN. Why? Well, we prove that this is irreducible. Yeah? Note that this little remark says that if you have any p-divisible group which is isogynous, then it is in here. Then it has this degree. So this space parametrizes really p-divisible groups, and all p-divisible groups isogynous with x appear as a fiber. So my favorite x0 there is one of the fibers, right? Now, you know there does exist a point where the A number is 1. Namely, the A number of GMN is 1. And as the A number is semi-continuous, the space where A is 1 is dense in every component where it does appear. But as it is irreducible, it is dense in the whole space. So your choice of the beginning x0 lives in the closure of the A equal 1 case. So it deforms to an A equal 1 case. Okay? So now, in order to convince you of the theorem, let me first show you an example, and then from properties of that example generalize to the general situation. So, definition of a semi-module, I'm not going to write it down because it's in the notes. A semi-module is a subset of the integers bounded from below, such that if you add m or add n, it is stable for that action. Right? And so that's a module over the semi-group generated by m and n. Right? And how do they appear? Well, suppose I have any map from any isogeny from x to mn. That means that the d of x sits in the d of hmn. Yeah? Let's call this m prime for a second, just to have notations. And observe that m prime has a filtration. It's a descending filtration. And this m sits in here. So I can intersect m with this filtration. And now I take all places where that jumps. So take all x such that positive integers, such that pi x m prime, this contains but is not equal to pi x plus 1 m prime intersected m. Now, I claim that this set is a semi-module. Clear, because if you have a gap somewhere and you apply Frobenius or you apply Verschiebung, that gap remains a gap, right? So, sorry, a non-gap. So that means that you have an element here which is not in there. Then if you apply that to that element Frobenius, right, it just raises this to n and raises this to n. So that means that if you have a non-gap, then there's a non-gap in x plus n and x plus 1 plus n. And the same for m. So this is a semi-module, right? So to such an isogeny, you associate a semi-module, right? Now, of course, I can always shift these things. I can, instead of m prime, I can take pi inverse of m prime, or I can pi m prime if it contains this. So I can shift this b by adding something. So I can change this to b plus a, which I baptize a. Right? And now it's a little technical condition. I say a is normalized if a is of the following form. Let me take the notation of the syllabus. A1, A2, AR, and all indices greater or equal to R. This seems strange, but let me do for you the exercise. What is the semi-module to GMN? What is B and what is A? Yeah? Okay, so let me do it for you in the case 5, 3. I have 0, 3, 5, 6. So adding 3 and 5 here, 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 etc. So I claim there are 4 elements, exactly R elements, which are below 8, and here everything is bigger or equal to R. Yeah? Now let me write down a little table for you for all semi-modules normalized in the case 5, 3. And I'm sorry, I'm now really doing some nasty computations, right? And that's what this is all about. Okay, so you have 5, 3. And you see, I have the semi-module 3, 5, 6, and I indicate the gaps. And of course, there are exactly R gaps. And then the next one is 1, 2, 3, 4, 6, 7. So you take, and I underline the generators, you take the semi-module generated by 1 and 8, and then you get these. And now the secret about this is that this automatically generates everything 8 and bigger. Now you take 2 and 4 and 5 and 7. Here's 2 and 4 generators. Then you take 2 and 5 and 6 and 7. You take 3 and 4 and 6 and 7. You take 3 and 5 and 6 and 7. And you take 4, 5, 6, 7. Now, I regret that Don Zagier is not in my audience, because he would immediately notice that the number here of such semi-modules equals to m plus n over m divided by m plus n, which is 8 times 6 times 5 divided by 1, 2, 3 divided by 7, and that's exactly 6, and that's exactly divided by 8, and that's exactly 7, and you have 7 things here. Right? Okay, so any such semi-module, I baptize A, if it is normalized, and I want to compute the following thing. I define a stratification of T by U of A is the set of points T in T such that the semi-module belonging to xt is A. Yeah? So what is a point in T? A point in T is such an isogeny that gives you the p-divisible group X, baptize it xt, that xt you map in some way to HMN, right? That defines you a semi-module by just this process, and then I shift it a little bit to get it normalized. Okay, now I'm ready to compute for you dimensions. So let me compute for you the dimension of a of UA. Please note that A is not in the beam variety. There are no beam varieties in this talk today, so A is just such a semi-module. So how do I compute this? So it's a very stupid thing. What you do, you take E0 plus a first variable times E1 plus a second variable times E2 plus a third variable times E4 plus a fourth variable times 7. Yeah, so I take any elements x1, x2, x3, x4 in some ring containing K, and I postulate a JDNA module which is generated by this element. Right? And over a perfect field, this is a nice JDNA module. You compute its A number, and if A number is of course 1 because it's generated by one element, and you claim that this element is exactly in UA, where A is this thing, and conversely, any point in UA, right, is of this shape. Proof, it's generated by one element, so you can write it as E0 plus sometimes times E1 times sometimes times E2, etc., 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 right? But you can erase the E3 because E3 is the F of E0. So if you see something at E3, you just subtract F times the generator times a constant, and you chase it away. So the point is that all gaps in the sequence give a dimension, and my claim is the dimension here is 4. Aha, that we knew already, because this is the A number 1 case, and that's dense in the moduli space, so that better be there. Okay, now here I do the same thing. Here is 1 as a generator, and 8 is not important, so here the dimension is 3. And you see what I do? I take the generator 1 plus x times x1 this, x2 this, and x3 this, and generator 8, and that gives me dimension 3. And this gives me dimension 2, this gives me dimension 2, this gives me dimension 1, this gives me dimension 1, and this gives me dimension 0. And I should indicate the generators in order to convince you. And also there's 2, 4, 5, yeah, that's, oh, this should be 3. And now why is this 3? You see, you get the JDNA module generated by E2 plus x1 E3 plus x2 times E6, and you get as new generator E4 plus x3 times E6. Yeah? You have 2 generators in the new module, and you get dimension 3. Now here the generators are 2 and 6. Here the generators are 3 and 4, so this should be 2. Here the generators are 3, 3 and 5, and 7, right? And here 4, 5, 6, 7. Aha, by the way, this shows that if you take a p-divisible group where the A number is the maximal possible, you might guess it is H, because this of course corresponds to H. But here you see a DNA module where the A number is 3, and which is not H. So that's definitely false. Yes? Yeah. So, for example, can I do it in this case? I take the DNA module, which is generated by E2 plus X1 times this gap times X2 times this gap plus E4 times X3 times this gap. Yeah? Now my claim is, if I have any p-divisible group which is isogynous to H, and where the semi-module normalized is this, then its DNA module is generated by two elements exactly of this choice for a good x1, x2, x3. And how do you do it? Well, you know the semi-module is this. So in there, E2, E4, E5, E7, and all higher ones do appear, right? The one having E2 as starting is one of the generators. This is the thing. With E4 is one of the generators, because these certainly are not coming from something previous, right? Then this generator is E2 plus a lot of garbage. But every time I see an EI, which is already in the sequence, I can subtract F and V multiples of generators to get away with that term. Yeah? So the claim is any p-divisible group isogynous to H with this semi-module is of this shape. Now, you might think that this is an easy thing, but there is, let me show you one example which really seems to destroy all this. So you have to be a little bit more careful than just doing this. Let me show you an example for A3. Yeah? And let me take the example where I have as a semi-module B something generated by 5 and 6, by 0 and 5. So what do I have? 1 and 2 are missing, 3 is there, 4 is missing, 6 is there, 7 is missing, 8 and 9, 10 is missing, and then I have everything bigger or equal 11. So you just do the exercise. You take 0 and 5, and then this is okay. So here the R is 2 times 7 and then a half, so R is 7, and 2R is 14, right? And now you see that this is not normalized. So in order to normalize, I must take everything at least 14, and then preceding, I must have exactly 7 of these. So 1, 2, 3, 4, 5, 6, 7. So this should be normalized to this. So the sequence really reads 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is missing, and 13. Right? Now what do I want to say? I want to say that the element E2 plus X times E6, 6 is a gap. Do we really want this? I want E4. And the element E7 plus Y times E9. Now this, under Verschiebung, maps to E. I made a mistake. 3, 5, 3, 5, 3, 5. No, that's okay. 3, 8. Oh gosh. I'm sorry. Yeah. So this adds 8. Yeah. So this belongs to. What am I doing? 2, 5, 7, 8, 10, 11, 12. Yeah, so this goes to E10 plus X tau E12. And this goes to E10 plus Y sigma E12. So my old trick of finding a generator plus all the gaps, in this particular case there are no relations, but here all of a sudden there's a relation appearing. So you can choose this plus this as X, you can choose this plus this as Y, but then there's a relation between this X and Y. Now, there's a whole section in our paper on the combinatorics of this, but that's really a little bit hard work, but it's okay. Now please go with me to page 57. There are a few conditions on saying that A is normalized, and I'm not going to write it down, so it's a subset of the non-negative integers. There are exactly R elements smaller than 2R, and from 2R everything is there, right? And then I take this UA, yeah, and then I have a little lemma, which is the proposition 710. And the proposition 710 says that the A is generated by one element, even only if the A number is 1, and that's what is there. Then the next statement is that this UA is geometrically irreducible of dimension at most R and strictly less than R if you're not in this case. So that's the proposition 710. And that proposition is an awful computation. Right? Okay, now you see that the U generated by 0 is irreducible because this is just affine space of dimension R. So this is irreducible, right? Now it could be that T is a union of T prime, union T double prime, where this is the closure of U0 and this is something else. Now if this would be the case, right, everything would collapse. Because if you take a point in T double, not in the closure of E0, for that point, certainly the theorem is wrong. So everything fails. But mind, I do know that if this is the case, that the dimension of T double is strictly smaller than R. Right? So this is the important case. Okay, and now I finish in just a few lines, and that's all the theory. Johann de Jong proved the purity theorem, which says that if a nutri-polygon, if your p-divisible group moves over a base, and if the nutri-polygon jumps, it's in codimension 1. Now that's highly implausible, because what are the number of equations of nutri-polygon strata? I showed you yesterday how to do that with crystals and then exterior power. So the number of equations is enormous. Why should a nutri-polygon jump in codimension 1? Well, because that happened in all the cases I saw, so all of a sudden I thought this must be the case. And then we set out proving it, and we did prove it. Now I know two proofs of that theorem, and both proofs are very involved. One is in the paper of Johan de Jong and myself, and one is in the paper of Hazio, which is completely different ideas, and I checked that proof, and that's completely correct. So now we have two proofs of this, but none of the two proofs is trivial. But it proves exactly this. Because what you easily see, and that is that picture which I have up there, right? That picture of the Newton polygon, you compute the minimal dimension of components of T. Now on T you know the Newton polygon. You know the total space of the deformation space, and you know the number of points lying strictly below this Newton polygon. And that number of points is an upper bound for the codimension. Because the generic point has the ordinary locus, and every time the Newton polygon goes down, you either stay the same or it jumps by dimension 1. So the number of jumps is exactly the number of lattice points up there. And now what you prove is that this dimension, which is R here, is exactly the codimension is, I mean, the difference between R and between the ordinary stratum is exactly the number of lattice points, and you compute it, that's exactly this dimension. Is it possible that there's a component of lower dimension? No, that will contradict purity. So this component doesn't appear at all, and then you have this, and you've proved your theorem. Now, if you want to do an exercise, and then I'll quit, do the following exercise. Take any of these things here. For example, this one. Yeah? You take your favorite x1, x2, x3 variables, or in some ring, or whatever. And you even may do it over a finite field, right? Then the theorem says that this JDA module, or this p-divisible group, is in the boundary of this. So if you have these x1, x2, x3 specified, say in a finite field, one is 1 and the other is 0 and the other one is 1 or something like that, I mean in a trivial case, then you should be able to write out variables x1, x2, x3, x4, specify the variables to these values in such a way that this module degenerates to this module. Mind the space is compact, mind the space is complete. So you really have to do variables here, specify them in some rather difficult way, either to finite values or infinite values, and then achieve that this specializes to this. Now that I did for months in a row to compute all these, and I never got any feeling for it. You see, this case is rather simple. In this case, you prove everything. But this case is already getting much more involved. Okay, so that proves the theorem we had in mind. And for today, I thank you very much for your patience. Thank you very much.